So we're now halfway down page 13, and we've gotten to something which is completely new to you. You haven't seen this before. It's called the Mass Spectrometer. What the Mass Spectrometer is, it's a piece of equipment, a machine, that chemists use to give you the masses of elements and compounds. Because we've just talked a lot about relative masses and mass numbers, and the thought might have crossed your head of, well, where do we get these mass numbers from, or work out how heavy different molecules are? This machine is what gives us a lot of information about the masses of things. Now, obviously, you've got a diagram here, it looks quite complicated. Lots of the workings of machines just isn't examined, it's not on the specification. So you might think, well, we can just skip it. What we find though is you find it generally a wee bit easier to understand the information in the questions about mass spectrometry if you know a little bit about how the machine works. So the questions are generally about the graphs you get at the end of using the machine, but I'm going to go through very quickly just a rough idea of how this machine works, because I think it helps you understand where this graph comes from. But anyway, going back to the start, just introducing it, the mass spectrometer is an instrument, which means a machine, used for two purposes: to measure the relative masses of isotopes, or compounds, can be used compounds as well, and to calculate the relative abundance of the isotopes in a sample of an element. What that means is it gets you two bits of important information. So let's say I put some atoms of chlorine into the mass spectrometer. I didn't know anything about the chlorine, the mass number of different isotopes or anything. The mass spectrometer would give me two bits of information. It would tell me if there were different isotopes of chlorine, it would be able to separate them out and their masses. So it would tell me there's an isotope with a mass of 35 and also my isotope with a mass of 37. That's one thing it does, is it weighs atoms or compounds, as we'll see later. The other thing it does, which is quite important, is it tells you how much of each isotope or each compound you've got, so the relative kind of abundance. So the machine would also tell me of the lighter one it's 75% abundant and the heavier one is 25% abundant, which is kind of the information you use to work out relative masses, but it comes from this machine, it comes from the mass spectrometer. So two things it gives you: different masses and weighs them for you, and also the percentages of each kind of species in your sample, so how much of each there is. In terms of how the machine works, there's kind of 5 separate stages here. So let's kind of just quickly go through it. Again, I don't want to labour too much because it's not examined, but I think it'll help you understand. This is where you put your sample. So the sample is the thing you're trying to investigate. So let's just keep the same example. Let's say I'm putting some chlorine. I'm putting in speech marks because I'm imagining I don't know anything about the chlorine. Obviously I can look at the periodic table, but let's just say I didn't know what the isotopes were. I didn't know what the mass was. I'm just trying to put this sample in to see what happens. So it goes into your machine. Chlorine's already a gas, so it just goes through, but I might have to vaporize it, which means turn it into a gas to make it work. And it gets fired into the inlet here. The first thing that happens is known as ionization. So you're turning it into an ion. The way we turn it into an ion is we bombard it with electrons. So it's called an electron beam. Bit of a new kind of thing, it's a bit physicsy, but if you hit electrons into atoms, it generally allows electrons to be knocked out. So you skipped on a wee bit here. It's kind of an equation form here. Here's an atom, you're bombarding it with an electron. That pushes another electron out, so now you've got 2 electrons, and leaves you with a positive ion. So it's a way of making it have a positive charge. The reason that positive charge is important is it allows you to accelerate your molecule, because as you remember, if something has a charge, it's attracted to things with an opposite charge. So you've got what's called a voltage gate here, which has a positive end and a negative end. The positive ion you've now got, which you've made, is going to be really quickly attracted to the negative end because it's got an opposite charge. So the molecule or the atom is going to speed up loads in this stage here. It's going to be accelerated. So it's going to be fired out or bombarded at the other end. So it's going really quickly now. And what should happen is it's just going in a straight line and hit the edge of the machine here. But as you see from the path, it's been deflected or pushed around a corner. The thing which is pushed around the corner is this thing called the magnetic field. So it carries out something called deflection. In the same way that things with charges are attracted or repelled by other charges, they can also be attracted or repelled by magnetic fields. So imagine it's like a big magnet. This magnet's set up to repel things with positive charges. So it's going to push it out so it doesn't hit into this wall and push it around this corner. Now this is the clever bit about the mass spectrometer. What you see here is you had one kind of beam of particles going through, but what you might notice here in this diagram is it's now split up into 2 beams. The reason it's split up into 2 separate beams is different masses are deflected by different amounts. If you imagine, if you were trying to stop a ball rolling down a hill, that'd be quite easy for you to do because it's quite light. You just put out the hand and stop it. But if you're trying to stop a car rolling down a hill, it'd be quite hard because it's so heavy. So you have to put a lot of force into it to change its movement. Same with atoms. A really light atom or molecule, you will be able to deflect quite easily. So that's the sort of first beam here. It's been bent quite like an acute angle, being pushed very easily, and it's going to end up this end of the machine. Something a bit heavier though will take a lot more persuasion to actually move around, so it actually doesn't bend as much, ends up hitting the corner of the machine here. Along this sort of edge of the machine is a detector. The detector is basically like a balance or scale that measures where different particles come and also gives you how much of each, the abundance of each one. Because what you might notice here is the first beam has got a few particles and the second beam has got lots of particles, so it's much more abundant. So after all that, after you've sped up your vapour, ionised it, accelerated it, deflected it and detected it, what you get is a graph. And the graph gives you all the information you need. So sticking to chlorine, what this would tell me in the graph, I know it's not got numbers on it, but if it did, it would tell me that this is a mass of 35 and this is a mass of 37. That's not actually quite right, but pretend it's correct. What this would tell me is that this 35 is least abundant and this 35 is most abundant, and I might have percentages. Obviously my example is broken down here because that graph's the wrong way around, but we'll just go with it. It gives you the height of each bit on the graph, gives you abundance, and its position on the x-axis gives it the mass. So again, that was quite quick, but it's quite a quick overview of how the mass spectrometer works. What we're going to focus now on is like how to actually do the questions, or what could be asked about the mass spectrometer. So there's information down at bottom page 13. Not going to read through it now because I've covered lots of this in my explanation there, and this stuff about molecular ions we'll come back to later on. So I'm going to leave it for now, but I will come back to it. So this is kind of what the question kind of revolves around. So this is a proper graph you might get in an exam with proper information on it. So just analysing what you actually get in the graph. So the y-axis is probably easiest to understand. You get relative abundances as a percentage. So the most abundance is 100% down to 0%. And the height of each line tells you the percentage of each isotope, for example. So this one's 18.7% abundant. This one's 81.3% abundant. So there's more of this one than this one. Just a little aside of that point, just something that can catch people out. Very occasionally in the exam, for reasons that's hard to explain, sometimes the scale lines up so they're actually the tallest one is made into 100. I think I can see that on the next page. Like, not worry about this graph, but just see that this tallest peak actually matches up to 100. What that means is that your total percentage might end up being more than 100, which can affect your calculation. But we'll not worry about it for now. I'm just flagging it up that it should be adding up to 100, these peaks, but sometimes they scale everything up so the tallest one's 100. But anyway, so y-axis gives you how much of it there is. This axis here, it's the m/z axis. Sounds a bit confusing. It's actually officially called the mass to charge ratio. So mass divided by charge. At AS level, it's kind of safe to assume that any ion, which is going through your mass spectrometer, has a 1+ charge. So if you're doing mass over charge for this axis, and your charge is always +1, generally it's just going to cancel down the fraction to be just mass. So you're safe to assume that in AS level, if you see an MZ axis labelled, it just means the mass. So for example, in this one, that's a mass of 10 for this isotope. This one isn't actually labelled, but it should be 11, and that's the mass of the other one. So you've got masses of isotopes and how much of it there is. What you could be asked is actually something we've done a lot of already, working out relative atomic masses. So from this graph, this is for boron, it's actually an example we looked at earlier, you could tell that it's got two isotopes, boron 10, boron 11. Boron 10 has abundance of 18.7, which is a bit more accurate than the figure we used earlier, and boron 11 has an abundance of 81.3. That's identical information that we've used before to work out relative atomic masses, and you do exactly the same sum as before. The mass times the abundance plus the mass times the abundance divided by the total abundance. Just to flag up again, in this case it was nice and simple because that actually adds up to 100. Just be wary, in case they give you a funny graph, if they'd scale the tallest one up to 100, your bit in the bottom would actually add up to more than 100. Sorry, I'm going to make that a bit clearer. So for example, they could have maybe given it as this having a percentage abundance of 100, and this one might be like 23. So you do your equation, it would be like 11 times 100 plus 10 times 23, and you would add up the total would be 123. So just be wary, it's not always going to add up to 100, the total. That's what I'm trying to say here. Should do if the percentages, but might be more than 100. So after all that, let's have a go a couple of questions. Pretty much actually are the same as ones we've done before, but we're just applying it to mass spectrometry. So this is an example. If you used xenon and mass spectrometer, it would actually give you 5 different isotopes from 129 up to 136 and the percentage abundances. Copper, we've got a slightly trickier example. You're given the relative atomic mass of copper, 60.5, so you kind of been given the answer, but you've not been given the abundances of the two isotopes. So you have to kind of work backwards to work out what the abundances are. So have a go. It's nothing different from what we've done in the last video. But see if you can have a go at calculating the answers to these two questions, and I'll go through the answer with you in a second. So the first one, I don't want to say simple, but there's no tricks to it. You've got a large amount of data to kind of work through. So same as before, you take the mass of one times by its abundance, then add all the rest together. And the bottom, it's actually adding up to 100 because the percentages. Probably would suggest just making sure, so you type in your calculator, add all those numbers up and just check it actually is out of 100, and that goes in the bottom. That should give you an answer 131.6. At this point, just one wee common sense thing to sort of bring up. Obviously with this like length of calculation, it's very easy to make a wee calculator error and get the slightly wrong answer. Whilst you can't guarantee the answer in your calculator is definitely correct, unless you've done the calculation correctly, there is a way of trying to work out if you've done something wrong. Because if you think about it, if we're trying calculating the relative mass of all these different isotopes, your answer should be between the lightest one and the heaviest one. So in other words, if you got a number lower than 129, that couldn't be right because you can't have lower than the lowest mass isotope, and similarly it couldn't be above 136. So our answer here, 131.6, is definitely somewhere in the middle of that, which gives you an idea it's not definitely wrong. Obviously it doesn't tell you it's definitely correct, but it sort of stands out, it's a reasonable answer. That's something to check in these calculations. Now B is a little bit trickier. So I'm going to talk you through it. So it's a little bit of algebra work almost. So what you've got here is two isotopes. So you've got copper with a mass of 63. Haven't got a percentage for it, just going to call it X. And we've got another one, 65, and haven't got a percentage for it, so we're going to call it Y. We're probably going to say it's percentages, so we're going to make it out of 100. And then when you do that sum, you end up with 63.5. Now, you may have done that and probably got stuck because you think you've got two variables here and you can't kind of solve that with just one equation. You have to use those simultaneous equations. Not so. There's a little trick you can use. There's a relationship between X and Y which we can use here. They're not just two random numbers. X plus Y add up to 100. So in other words, so if I write that down, I'm able to get one in terms of the other. So if I wanted to say what Y was, Y is just the same thing as X minus 100, because that's just the difference between them. I can solve that into my calculation. So now what I've got is just everything in terms of one unknown, in terms of X. I can solve that for X a bit more easily. So taking that 100 around the other side, so I get 63X plus 65 upon X minus 100 equals 6350. I'll expand that bracket, 63X plus 65X minus 100 equals 6350. Then I maybe combine my X terms. In fact, I've made a horrible mistake. Just going back here, sorry, right up here, should have been 100 minus X. It's probably a lot of you spotted. Apologies for that. Doesn't affect too much. Sorry, this line should therefore be 63X plus 6500 minus 65X, apologies for that, equals 6350. So combining my X terms, it comes out as minus 2X equals minus 150. In other words, 2X equals 150. Therefore, X equals 75%. And converting that into Y, just taking from 100, Y is 25%. So sorry I muddled up a wee bit, but it's using a wee bit of algebra to try and work out an unknown percentage. That's on the trickier end of questions. I've not seen one like that come up in an exam, but definitely could. So keeping track of what we got to, so we looked at the mass spectrometer, we've looked at how it gives you information about isotopes and abundances, and that means you can just do the same calculations we've done before, just off a graph to work out relative atomic masses. There's two more things that you can use a mass spectrometer for we're going to touch on here. So that's on page 15. First one's for diatomic molecules. So the question is, okay, well, if you put an atom in, it gives you masses and isotopes, etc. What about if you actually put a molecule in? So an example would be Cl2. That's the classic example we look at. So think about Cl2. It means it's a chlorine bonded to chlorine. So the same thing will happen. You go through mass spectrometer, ionize it, accelerate it, deflect it, detect it. But what you end up with is a slightly confusing looking graph. It's got lots of peaks on it, even though you've only put one individual thing in it. So you need to break it down and try and work out and try and be able to explain why you get this unusual pattern for chlorine. So the first thing that we've got to worry about is with chlorine, obviously, it's got different isotopes. We've touched on it a few times already. Chlorine has a mass of either 35 or 37. So if we think about the different types of chlorine molecule we could make, so ClCl, ClCl, and ClCl, there's actually three different combinations. I could have a really light one where I've got a 35 and a 35. That would have a total mass of 70. I could have an in-between one, which is a mass of 35 in one chlorine and a mass of 37 in the other chlorine, which gives me a mass of 72. And then I could have the heavy one, which is 37 and 37, which gives me a mass of 74. So that's three different versions of the chlorine molecule I could get, just depending on just random chance which chlorine isotopes end up in which position in the chlorine molecule. So in our final spectrum, which comes from the mass spectrometer, we see these three peaks here, which correspond to 70, 72, 74. So that's our three Cl2 molecules, just of different masses. So that's all some of the issue. So we know why we got these three peaks here as opposed to just one. We got different chlorine isotopes in the molecule. Doesn't explain these two peaks here, because those are the only combinations we could have. The reason we got these two peaks is another thing that can happen in the mass spectrometer called fragmentation. Fragmentation, as you maybe can guess by looking at the word, means breaking apart. So when you've got a chlorine molecule, just because it's quite high energy in the mass spectrometer, there's quite a lot going on, bonds can break. And when bonds break, you get individual atoms separated. So that can happen to our chlorine molecules. So depending on what we had in the molecule, we can have two different types of chlorine atom. We have a chlorine atom with a mass of 35, which is this peak here, and a chlorine atom with a mass of 37, which is this peak here. So whenever we put Cl2 molecules into the mass spectrometer, we end up with a complicated spectrum for two reasons. One is for the molecule section here, we got three different peaks because we got three different combinations of isotopes. But also down near the bottom, we see individual chlorine atoms showing up because the chlorine-chlorine bond can break in the mass spectrometer and separate the different atoms out. So really important thing to know for chlorine, because this comes up quite a lot in the exam, is knowing that you should have 5 peaks for the mass spectrometry experiment for Cl2. And you should be able to justify why you've got those different peaks. Don't need to worry too much about the height of the peaks. Now, I know you do see that. The most abundant Cl2 will have the two 35s because they're the most abundant chlorine, but you don't need to worry about any calculations about why they've got different heights. And you should remember the chlorine 35 is the most abundant one compared to 37, so that one's higher than that one. But the main thing is knowing the position of the peaks and knowing how many you're meant to get. And the last thing very quickly is the mass spectrum of big compounds. Now this isn't actually something you touch on that much in AS, it's more of an A2 upper 6 topic, but there's one wee thing you need to know. So this is imagining if you put in like a massive big organic molecule. For example, I think this peak is or the spectrum's for ethanol, C2H5OH. So that's obviously got lots of bonds, lots of atoms. You end up with a much more complicated spectrum. You see lots of peaks here for the same reason we saw these two peaks for chlorine. Fragmentation takes place in the mass spectrometer. So in other words, bonds break, you end up with smaller fragments. A couple of features you're meant to know about the compound spectrum. The one on the very top of the spectrum, so the biggest mass, is known as the molecular ion peak, because that's the peak that corresponds to the whole molecule going through. So nothing's been broken up, nothing's been fragmented. So the peak with the highest MZ value, so highest mass value, is called the molecular ion peak. So maybe you might be asked an exam to label that peak. It's called the molecular ion peak because it's got the biggest mass, so it corresponds to the whole molecule that hasn't been broken up. The only other one that we maybe could ask about is the base peak. The base peak is the most stable fragment. So if I broke this ethanol apart a wee bit, I get to this fragment which has a mass of 31, and that looks like the most stable one because it's got the highest abundance. So molecular ion peak is the biggest mass, The base peak is the most abundant peak in the spectrum, and that's pretty much it.